My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 459. In this lecture, we will try to understand ransack. So, now we will learn a very interesting concept called ransack. Ransack stands for random sampling consensus. This is a concept in statistics which is used a lot in modern machine learning. What it tries to solve is it says, can we build a machine learning model, any model for that matter, in the presence of outliers? How do you build a robust model in the presence of outliers? What is a robust model? A robust model is a model that is not impacted by the presence of outliers much. How do we achieve that? So, ransack is a very elegant, superb solution used in the area of computer vision, which is the area of intersection of image processing, which works about processing images and machine learning, because there is lot of noises and outliers in images. So lot of real world problems in computer vision, ransack is a very popular algorithm. So let's try to understand this. Can we build a robust model in the presence of outliers? Here, for the model, we simply take linear regression as my model, so that it is easy for me to explain it graphically. So the task is, I have data set like this. Let me assume this is my data set. Now let's assume this is my xi. Just see, let me say this is my xi, isn't it? And what is this? And this is my yi, and I have bunch of points. So in linear regression, what is my goal? What is the goal of linear regression? My goal is to find a line or a plane that fits most of the points. So imagine this is my data set. All these points, which points? All these points, otherwise let me say all these points, yes, all these points are in layers, and all these points, and these points, all these points, circle points, let me say, are outliers. What is the ideal plane that we expect out of these points? This is the plane, isn't it? This is the ideal plane. This is the plane, isn't it? This is the plane that we expect to be written. This is my ideal plane. Call it as L star. This L star is my ideal plane, or L star, or the ideal line. But what happens is, let's assume this whole data set is called D train. This whole data set is, let me assume, D train, which is basically set of xi comma yi, isn't it? Where xi is just a number and yi is also just a number. Xi belongs to R and also yi belongs to R. That's why it is called regression problem. Your xi belongs to R, yi belongs to R, therefore it is a linear regression. Now if you train linear regression model on the whole of D train, probably the line that we get is like L1, isn't it? L1 probably looks like this. What is my L1? This is my L1, isn't it? This is L1. So what is the linear regression? Linear regression try to minimize linear regression. What is the idea in linear regression? Linear regression is saying, I want to minimize square distance sigma equal to 1 to n yi minus yi hat whole square. This is your squared loss. You are trying to minimize, you are trying to find w, where what is your yi cap is nothing but w transpose xi, isn't it? That is x. You have to minimize sigma equal to 1 to n yi minus yi cap whole square. This is what you are trying to achieve in linear regression problem. You are trying to minimize squared loss, isn't it? Problem is what does it mean? What is the intention here? Here problem is some of these points are so outliers. Imagine there is an extreme outliers. Let me assume these are outliers. Problem here is there are some extreme outliers. This is outlier, this is outlier, this is an extreme outliers, isn't it? Extreme outliers here, outliers, even you can find outliers with particular distance. This is the this particular outlier is far away from this line, isn't it? From this is a way far away from the line to be constructed, or from original line. What happens is, if your extreme outliers on one side, just see, you have outliers on you have outliers on both the sides, isn't it? Just see, this is, if you observe here, what's happening here, you have outliers, here also you have outliers, but this side you have more number of outliers, this side you have less number of outliers, isn't it? The extreme outliers tends to pull the line towards them. This L1, this line is pulled towards them. Why? Because here you have more number of outliers. I have some outliers here, few outliers this side, but these outliers are fewer outliers and less extreme. You have less extreme outlier this side, isn't it? Less extreme outliers compared to this side, isn't it? Less outliers than what I have outlier this on this side, isn't it? That's why these extreme outliers are pulling. Just see, they are pulling towards these extreme outliers, isn't it? That's why they pull the hyperplane towards them, especially more extreme. This side is more extreme outliers, therefore they are pulling the line towards them. So that L1 that you got is non-robust model, because it is impacted lot by outliers. This particular L1 is impacted lot by outliers, therefore it is non-robust model, especially because of these extreme outliers. Now the question is, can we come up with a neat mechanism to avoid this whole problem of impact due to outliers on the model itself? So what RANSAC does, it is very cool trick. So it says, first it says, remember you are given D-train. Let me say you are given D-train data set. So it says, first let's take a data set D0. What is my D0? Which is random sample of points from D-train. Your D0 is random sample of points from D-train. That's why random sampling word coming from this particular RANSAC. In RANSAC, RAN means what? Random. You are taking random sample because you are taking a random sample of points from D-train. Therefore, what is that random sample of point? Random sample of points from D-train. You are saying that as D0. On this D0, let's build a model. Let's build a linear regression model which results a line L0. What is this? We are building a model L0. When I sample, most points are going to be, if I take samples, what happens? When I sample, most points are going to be inlayers. Outliers are going to be fewer points. You may have one here. What is this? You may have one outlier here. You have one outlier here. What is this? One. Yes, this is one outlier. This is one outlier. This is one outlier. This is one outlier. So when you sample bunch of points, let's assume we sample let's assume we sample 50% of the points. When I sample 50% of the points, the probability of outlier being part of my D naught, the probability of outlier being part of D naught reduces to 50%, isn't it? If I sample 50% of points, most of the points come from where? Most of the points come from here, isn't it? Why there are so many inlayers, isn't it? Most of the points will come from inlayers. Of course, out of these 5 outliers, how many outliers? 1, 2, 3, 4, 5. I have 5 outliers. Out of these 5 outliers, I may get 2 or 3 outliers. If I take 50% of the points, I may get 2 or 3 outliers. But the probability of an outlier points being present in D0 is reduced by sampling size. Now, when I build a model from sample data, let's assume these points. Let's assume these points. Let's assume these points. This point, 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 this point. Let's assume these points are not in random sample. They are not in my random sample D0. So I strike out of these points which are not in my sample. Now when I build a linear regression model on top of it, I would get a line. I will get a line which is less impacted by some outliers, and not all outliers. So if I build a model with everything, I would got a line L1, isn't it? If I built a model with everything, I have got a model L1, which is much more farther away than if I built on sample of points, and this is my L0. This L0, if you compare L0 and L1, this L0 is built on sample of points. This L1 is built on original data set. This compared to L0, this L1 is more farther away from ideal line. This is first step. Second step, I will compute outliers based on my model L0. And how do you compute outliers? Basically, take distance of each of these points and take the difference of yi cap and yi, isn't it? I have to take difference between yi minus yi cap. Those points which have high yi minus yi cap, let's call the set as O0. This is O0, isn't it? Which is set of outliers that you have from D0. We can compute all the outliers in all the data. We need to compute outliers on the total data D train. Here you are computing outliers on total data set D train, isn't it? On the total data set D train, compute the outliers. Once you got these outliers, what you do is you construct the next data set. Let's call the data set as DTR1. DTR1 is DTR minus O0. We know the set difference, isn't it? DTR is one set, O0 is another set. The outliers detected using model L0, we are removing from the total data set. You are removing from total data set, that is DTR. Now, next step is what do you have? DTR1. You have now DTR1, where we removed some outliers and not all outliers. We removed some outliers, not all outliers. Now again, we construct a data set. D1. Just see, we are constructing a data set D1 by taking random sample. Again, you are taking random sample from where? from DTR1 and build a model. You are building a model L1 on top of it and find outliers O1 in DTR1. You have to find outliers in DTR1 using the model L1. You have to find outliers using the model L1. Now you construct a data set DTR2, which is DTR1 minus O1. Now on this again we construct D2. Again what you have to construct? We have to construct D2. This is D2. D2 by removing, by random. How can I construct this D2? By random sample. By random sample, and you train model, you have to train, this is D2, you have to train model L2, isn't it? And use the outliers again, and using that we can compute DTR3. Again you do random sampling, so on and so forth. You keep doing this till the time. Let's assume I got a model Li. Let me assume we got a model Li, isn't it, in ith stage, and Li plus 1 in the next stage, that is I plus 1th stage. Li and Li plus 1, if these two, Li and Li plus 1, if these two models are almost same, if they are almost same, if they are Li and Li plus 1, if they are almost same, if both are almost overlapping, I can say it is perfect and I don't have any more outliers in my data. And the final robust model built on DTR I plus 1. I have already removed all outliers. Initially, what we did? Initially, take whole training data. What we did? Initially, take all training data, DTR, take random sample of points. From this, you have to take random sample of points, build a model on top of it. What is that model? I am saying, let it be, build a model on top of it. Use this model to find outliers on the D train. Use this model L0 to find the outliers on DTR. Remove these outliers from DTR, isn't it? Now, just name it as DTR1. So from this data set, we remove from this data set DTR, we are removing outliers. Now on this model, again what you are doing here, you are constructing on the, again perform sampling, you are taking sampling. Just see again what you are doing, take random sample, again build model L1 and find outliers in DTR1, find outliers on DTR1, again construct DTR2. How can I construct? DTR1 minus O1, removing all the outliers which we found on the previous iteration, Now on top of this, you have to construct this is my DTR2. You can actually sampling it again this DTR2, again take random sampling, construct a data set D2, D2 and build a model L2, isn't it, and find out outliers O2 and removing these outliers from DTR2. You remove O2 from DTR2, isn't it? Just remove these from DTR2. Then we get DTR3. Keep repeating till the time your model that you got in the ith iteration and I plus 1th iteration are very similar. Once you done that, you say it is, you can say if they are similar, I can say it is converged. It is converged because there is no more change. There is no more change in data. So finally, at the end of the iteration, you will get DTR I plus 1, isn't it? The final robust model. Now you train a final L star. I can say this is final L star model on top of DTR I plus 1. This L star is robust model. this is how ransack works. Very interesting technique. Just go through it. If you have any difficulty, please keep a comment. Thank you very much.